So we'll be talking today about smart dampers or smart stack dampers. Bala has already given a little bit brief about the company. We started this journey in 1996. We currently have 3 offices worldwide. Our main office is in Sugar Land, Texas. And then our engineering office is in New Delhi, India. We started that in 2005. And we have a fully dedicated CFD office in Pune, which was started in 2014. Furnace Improvements totally has about 45 people on board. And our mission is to improve the performance of existing furnaces. We are the only heater company that focuses on revamping existing fired heaters, and 90% of our business is revamping fired heaters. Our model is working directly with owners and end users, typically doctor-patient direct relationship. And we try to provide unique value-added solutions. Our philosophy is do it once, do it right, and do a very high quality technical work. That is typically our philosophy. We have 3 patented technologies. Our approach has been a contrarian approach. We have always challenged the conventional way of doing things, and that is how our patented technologies came out. Our first technology, split flow, is basically parallel feed. Typically in fired heaters, the fluid first enters the convection section and then the radiant section in series flow. And we challenged that and we came up with the split flow, which is parallel processing. And we have the fluid, part of the fluid going into the convection section, part of the fluid going into the radiant section at the same time. We have almost 15 installations. Next technology is inclined firing. And as you know, in most of the fired heaters, the burners are firing vertically up, mostly in VC heaters. And we challenged that and we said, why can't we fire them inclined actually? We can fire them inclined towards the center. And we installed several installations. And we found that we are able to reduce the flame impingement and lower the tube metal temperatures as much as by 200 degrees. And similarly, the last technology the one which we are going to be presenting you today is smart stack damper. And we found out that most of the stack dampers are not working and the operators are frustrated, the owners are frustrated. So we started looking at it and doing a root cause analysis. And that's how the smart stack damper was born. So that's what we will be presenting. This is a list of our clients. Most of our business has been in the US, even though we have performed in Europe, Middle East, and in India. Most of the business which we get is repeat business. We have clients with whom we have been working for almost 20 years, and we are almost like their in-house engineering company or a heater revamping company. We want to take this opportunity to thank all our clients for their valued business. So what is smart stack damper actually? I mean, let's talk about it. And our concept is very simple. We are customizing the stack damper to suit the furnace on which it is installed on. So it is providing a tailor-made control specifically sized for your fired heater, specifically sized for your stack, and it works. It provides safe, reliable, operator-friendly draft control in fired heaters. That is basically the smart stack damper technology. It's a very simple concept. So our agenda today, we will start with an introduction of fired heaters. We'll talk a little bit about the combustion process. Then we'll look at how the stacks are designed and how the dampers are designed and installed. And we'll talk about smart damper design features. I have two case studies that I want to present to you. And in the end, we will have the cost benefit analysis. What is the typical payout time for these dampers? So I'm presuming most of you are familiar with fired heaters. Most fired heaters have three major components: radiant section, where bulk of heat transfer takes place, and that's where the burners are located. Then we have the convection section, where the rest of the heat recovery, or about 30% of the heat recovery, takes place. And then we have stack, which safely disposes the flue gases to the atmosphere. The fired heater is only equipment in the industry where open combustion is taking place. We are burning fuel gas with combustion air to generate heat. And this heat is getting transferred to the process hydrocarbon fluids in radiant and convection section. And then the flue gases get vented through the stack. Fired heaters are the largest consumer of energy in a refinery, and that is one reason why we want to minimize fuel consumption or maximize our efficiency. Let's talk about typical operating issues in fired heaters. There are several issues. Uh, Safety is one issue, of course. Whenever you have a combustion upset causing high pressure at the arch, it can do this thing. Efficiency has always been a major issue, even though currently the energy prices are low. We are always worried about tramp air and high excess O2 operation in the fired heaters. Reliability is also a major issue. The run length, flame impingement on radiant tubes, insufficient air or short run lengths. And then the NOx emissions. Sometimes if you have high excess O2, you can get into high NOx emissions. And if you look at all the four major operating issues, you see they're all finally boiling down to the combustion, how good our combustion is. So our objective, whether you are a operating engineer or heater operator or technical service engineer, our operation is to get the best, our objective is to get the best combustion in fired heaters. I want to spend a couple of minutes on the combustion. Combustion is an oxidation reaction, a very irreversible reaction where fuel, which has carbon and hydrogen, combined with oxygen, which is present in ambient air. And when they combine, they produce heat and then they produce flame. And what we are doing is we are transferring the chemical energy in the fuel into thermal energy of heat. Uh, Typically, 2/3 of the operating cost in heaters is the fuel cost, and that is why you want to have efficient combustion in your fired heaters. So let's talk about efficient combustion. And in any typical process unit, the conditions keeps on changing, sometimes major, sometimes minor. So the fired heater load goes up and down all the time. Now, there are two components which we need to control. We have fuel gas supply, which is controlled by the fuel gas control valve. So we don't have any major issues there when we talk about fuel gas supply. And we have oxygen analyzers, which are installed to measure the combustion efficiency, how much excess O2 we are having in the combustion reaction. And we have a very good quality of oxygen analyzers available today in the industry. There are laser-based TDLS oxygen analyzers, and so we have been doing a very good job of measuring oxygen in fired heaters. But the issue comes, how do you control the combustion air, which is the final control element actually? You have measured the oxygen, but how do you control the combustion air? And that's what we will be focusing today in our presentation. So fired heaters have been designed all the time as an inherently safe equipment. And what that means is it is designed to operate at negative pressure throughout, so that anytime any operator or any engineer opens the PEEP doors, the flue gases don't come out. And the way we do it is we keep the arch, which has the highest pressure in the fired heater, at a negative minus 0.1 inch draft. And you can see over here, this is the arch where we keep the negative pressure of minus 0.05 or minus 0.1 inch. And then because of the radiant section height, we create draft, and that is a draft which is available at the burners, and it is used for supply of combustion air from the atmosphere. So this is where the draft driving force. And then we have the convection section pressure drop here. And again, we have the stack effect due to the convection section height. We have the damper loss, and then the draft is provided by the stack. And at the end, we have an exit loss. So if you look at it, the flue gas pressure drops, basically we have convection section pressure drop, damper loss, stack entry and exit loss. Frictional loss is already accounted in the stack effect. And these are the three stack effects: SC, A in the stack, C in the convection, R in the radiant. And draft is dependent on two parameters. It's dependent on the stack height and ambient air temperature. That is basically the draft which is provided. So as I said, the draft is dependent on the ambient air temperature. And as the temperature goes down, the draft increases because the outside air becomes a lot more denser. And you can have almost as much as 0.15 inch variation between day and night at the arch or draft in this thing. And the flue gas pressure drop is proportional to the firing rate. So most of the time, if you see at 100% load, the damper opening may be even less than 30 degrees. At 120% load, the design is typically at 45 degrees. So if you look at it, because of the ambient temperature variation, you have to at least operate the stack damper at least twice at any time the heater load changes. And our analysis shows that the existing stack dampers are highly oversized, and they are incapable of providing the draft control needed. That is what our analysis shows, and we will come back over here. Just to give you a little relationship between the arch draft and the excess oxygen, because most of the people are able to understand the excess oxygen very clearly, don't understand the arch draft, importance of the arch draft. So this is a tuning exercise I did several years ago in Europe. Okay, just a minute. Sorry for the interruption. I forgot to connect my laptop to the power supply, and it was showing me low battery. So when we have in this exercise, basically we have the heater, which was operating at minus 15 millimeter water column or 0.6 inch draft at the arch, and it was running around 5% oxygen. And all we did was to close the stack damper, and we closed the stack damper and went down to about 6 millimeter draft or 0.24 inch, and just by making one changes, we were able to lower the oxygen from 5% to almost close to around 1.5%. And this kind of improved the efficiency by almost like 3%, just single action by closing the stack damper. So stack damper has a direct control on the excess oxygen or the heater efficiency. And excess O2 can be easily controlled by maintaining a constant draft. I could have gone even more, but the operators were scared because even 0.24 inch is high as compared to what we typically this thing.